Video 23 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is time-dependent response theory. Now we finally have all the necessary ingredients to extend our treatment of time-independent response theory from chapter 3.3 now to the time-dependent case, the case where our system is perturbed by a time-dependent field. And again, like in chapter 3.3, we look at the expansion of an expectation value of some kind of operator, operator P here. And the difference to the previous treatment is now that our wave function is not only dependent on a field, which was time independent in the case of chapter 3.3, but now the field is time dependent and therefore also our wave function is time dependent. Now, right now, I will only look at an operator P, which itself is not dependent on the field. If we now expand this expectation value, where we essentially expand our time-dependent perturbed wave function using the results from our chapter on time-dependent perturbation theory, meaning we expand it in a time-dependent zeroth order wave function and a time-dependent first order correction to the wave function, and later on in this chapter also we will look at the time-dependent second order correction to the wave function. Now here I will only use the first order correction to the wave function. I've inserted that both here in the ket and in the bra. Then I end up with three terms. The first one where we just have the zeroth order wave function, the time-dependent zeroth order wave function, and then we get two terms where we either have the first order correction to the time-dependent wave function in the ket or here in the bra. And we can now insert our result for the first order correction to the time-dependent wave function from chapter 3.9 on time-dependent perturbation theory, which I have done in these two expressions. And you can recognize it here. So this part, the bra and the operator, is what it has here, and all the rest, this one, and the integration over time, or t prime, is our result for the first order correction to the wave function. And correspondingly, in the second term, where I have done inserted it in the bra instead of the ket. Now I can use several things. I can first of all use what is the expression for my zeroth order time-dependent wave function. And that is the time-independent wave function pre-multiplied or acted on by this exponential operator with the time-independent Hamiltonian. So this is sort of, it just describes the time dependence of this unperturbed wave function. I will do that here and there. Which then means, because I have this operator here, exponential operator, means that also my operator P of my property P here is sandwiched between two of these exponential operators, and with the exponential operator plus sign to the left and an exponential operator with a minus sign to the right. So here. Which means that this operator actually shows up also again in the interaction picture, or also called Dirac representation. So that's what I have here. Secondly, I have a minus sign here, which comes from the fact that I inserted my first order correction to the wave function, which includes an I in the bra, and I took the I out, so I get a minus sign. So, and I have here basically the property operator in the interaction picture, followed by the first order correction to the Hamiltonian, also in the interaction picture, and a second term minus with the other order, which means I actually have a commutator here in these, so I can write these two integrals together, just in one integral over the commutator of the two operators, the operator representing my property, which I look at, and the first order correction to the Hamiltonian, both in the interaction picture. Now the integral over time here which comes from the first order correction to the time-dependent wave function. That goes from minus infinity to the time t we're looking at, which makes physically, of course, sense, but it's not very convenient because later on we would like to make use of some Fourier transformation. Therefore, I would like to extend the integral now to go from minus infinity to plus infinity. But of course, I have to maintain what the value of the integral is, which means whatever I add from t to plus infinity has to be 0. And so I use a small method, or one uses a small mathematical trick. That one introduces this function theta here, which is called the Heaviside step function, which makes sure that whatever I add to the integral by extending the upper integration limit is actually 0. Because the definition of the Heaviside step function is that its value is 1 if the argument is larger or equal to 0, and is 0 if the argument is negative. And that means for all times t prime, which is my integration variable, larger than t, this Heaviside step function is going to be 0. So now I have an integral from minus infinity to plus infinity. Of course, later on when I carry out the integration at some time, I have to remember what the definition of this Heaviside step function is. The second thing what I want to do is now to insert my perturbation Hamiltonian, the first order correction to the Hamiltonian. And again, I write that, as we've done several times now, as the product of a component of the time-dependent field and what I sometimes call the perturbation operator, which is the part of our perturbation Hamiltonian, which depends solely on coordinates or canonical momenta, or in principle could also be spin of the electrons. And here, of course, because the field is a vector, or could be also a tensor, I also have the corresponding components here, and I have to sum over all the components. Now, this is an integral again. This in the Dirac notation is an integral over all coordinates and spin variables of all the electrons. And my electric field does not depend on any coordinates of the electrons, so I can take the electric field outside of the integral, what I've done here. Now the whole second term here, that is the time-dependent linear response of the expectation value of my property P to the time-dependent field. A time-dependent field which has been applied from minus infinity to the time t at which we sort of measure or look at our molecular property, or I look at our expectation value here. And this linear response, of course, is an integral over time, meaning the longer we apply the perturbation, probably the larger the response will be. And then it's a product of the time-dependent field and this quantity here in this curly parenthesis. And that quantity describes how susceptible our system is to changes introduced by the dependent field. I mean, how easily the expectation value for this operator is changed by an application of the time-dependent field. So if this quantity in the curly parenthesis is large, then the linear response of our expectation value to the time-dependent field will be large. If it's small, it's small. So it's quite an important property, and it got its own name. It's called the linear response function, and here in the time domain, and it actually gets its own symbol with these pointy parentheses. And a particular notation, because so it's pointy parentheses, a bit like, I mean, the kind of parentheses one uses for expressing average values, but now we have them twice. And there are two operators here in the linear response function. The first operator, which comes in front of the semicolon, that's the operator of our expectation value. So that is the operator which expectation value is perturbed, which linear response we study. And the second operator here, and I indicate that also with the notation P and O here, and the second operator is the perturbation operator. That's the operator in our perturbation Hamiltonian, meaning the operator which represents the interaction of our system, of our molecule, with the external field. So here I've written up the definition of this linear response function in the time domain. Once again, it's this expectation value over the commutators of our property and perturbation operator in the interaction picture multiplied by this Heaviside step function. In addition to the name linear response function in the time domain, it's also in some other literature, it's also called a polarization propagator in the time domain, and it's actually mathematically, it's just a double time Green's function. Now with this linear response function or polarization propagator, we can now write the expansion of our time-dependent perturbed expectation value in the unperturbed and also time-independent expectation value plus an integral over the linear response function or components of the linear response function multiplied with the corresponding component of the time-dependent field. And you can see here that there are two times. There is the time t at which we look at our expectation value. So that's the time we're interested. And then we have the time t prime, which comes from the integration from minus infinity to the time. So one might ask oneself whether this response function, linear response function, actually is a function of two times t and t prime. And the answer is no. And of course, physics tells it that it should be no, because if it would be a function of both times, this would mean that if I apply a perturbation to a system for a particular time period, and I would do that today, and I would do that tomorrow, and then I look at how much this application of the perturbation changed my expectation value, I might get a different result tomorrow, and that makes, of course, no sense. So let's see whether we can also show that this response function in the time domain actually is only a function of the time difference between the two times. Well, here's the definition of it. And let's write now the transformation to the interaction picture out explicitly here for the operator P, which I have here with the two exponential operators with the unperturbed Hamiltonian. Now, remember again that our wave function here, the unperturbed zeroth order wave function, are the eigenfunctions of this Hamiltonian. So I can let the exponential operator act on it a here to the left in the first term of the two terms which you have in the commutator. Remember, here's a commutator, so I have two terms, this one and the one interchanged minus the one interchanged. So in the first one, I can let the exponential operator here to the left act on my expectation value, I get the energy then, and in the second one, I can let it act on the right one, and then I can take this exponential out of the integral, and I can actually later on insert it on the other side again and go back to it. So I can move this one here over to the operator O, and also let this one, instead of to the left act on P, act on O, which means I will get this expression here. So in addition to the two operators which depend on time t prime, which I have here because the operator O is also in the interaction picture, I get a second one. So I can say that this is still in the interaction picture, but it's not with t prime, but it's t prime minus t, which means the time dependence here in the interaction picture is not t prime or t, but it's t prime minus tt, so it's the time difference. In practical applications of this expansion of our time-dependent perturbed expectation value and the properties we are going to define from that, we are often more interested in properties which are frequency dependent than the ones which are time dependent. So let's therefore define also here a linear response function in the frequency domain, and we can easily obtain that as the Fourier transformation of the linear response function in the time domain to the frequency domain. And in the exercises, uh, you will derive then what is the expression for this linear response function in the frequency domain. And the result is given here. And this looks very much similar to what we had as the second order energy correction in time independent perturbation theory. The big difference is that here in the denominator, we do not only have the difference between the two energies, the energy of the ground state and the energy of the given excited state, which we have here in this sum over all excited states, but we also have the external frequency or the energy of the external frequency h bar times omega here in the first term. In the second term, where the two operators are also interchanged, we have minus h bar times the frequency of the external perturbation. Now with this linear response function in the frequency domain, then we can rewrite our expansion of the time-dependent and perturbed expectation value, where again the first term is the expectation value of our operator with the time-independent unperturbed wave function, and then the first order term, first order in the field now, we write now in terms of an integral over all the frequencies instead of an integral over time from minus infinity to the present moment t. So we have now an integral over the frequencies here with our frequency dependent linear response function, and again also our external field we have now in the frequency domain, so we have frequency components here. Now looking at this expression here for the linear response function in the frequency domain, which was derived by assuming that we know the unperturbed wave functions, all the excited state unperturbed wave functions, we can identify some symmetry relations. The expression which we had here, I just set the frequency equal to 0. For example, one can easily show that if I interchange the two operators in the linear response function, and at the same time I replace the frequency by minus the frequency, then I get the same result. This is obviously two special cases. If you have two Hermitian operators, P and O, so our property operator and the operator representing the interaction of the molecule with the perturbation are both Hermitian operators, and if they are both real operators, then actually the response function for plus frequency and the minus frequency are the same, or the same if they are both purely imaginary, but still Hermitian operators, it also applies. And a purely imaginary operator, for example, would be the angular momentum operator or the canonical momentum operator. They are purely imaginary, whereas a real operator would be a dipole moment operator. Now, on the other hand, if we have, again, two Hermitian operators, but one real and one imaginary, and I interchange and I replace the frequency by minus the frequency, then also I get a sign change. Another thing which we could look at is how does this sum over states expression for our linear response function look if we take this frequency equal to be 0, which is called the static case. So our external field is a static time independent field then. Then of course and then I get this expression. And this is exactly what we had in some of the previous chapters on time-independent perturbation theory as being the second derivative of the second order correction to the energy with respect to two components of the field. Which means when we go to the frequency independent case, to the static limit, we return to the expressions which we had from time-independent perturbation theory. And you should note that a linear response function, meaning the linear response of an expectation value to a perturbation, corresponds to the second derivative of the energy. And this is quite clear because remember the Hellman-Feynman theorem that By taking the first derivative of the energy, you get to an expectation value, and then the second derivative is then corresponds to the linear response function. Now, so far I have assumed that my property operator P here is a perturbation independent operator, which basically means that the field would be an electric field. And I want now to extend that to the case of magnetic perturbations, where, remember, we had in the Hamiltonian not only a first order correction to the Hamiltonian, but we also had a second order correction to the Hamiltonian coming from the term where we had the vector potential squared. And for such a case, we had in the chapter on the Hermann-Fermi theorem, which was chapter 3.1, defined perturbation-dependent operator here, perturbation-dependent operator, which we obtained like any other of the property operators from the Hermann-Fermi theorem as the partial derivative of the Hamiltonian with respect to a component of the field. And if our Hamiltonian has first and second order contributions, meaning terms which are linear and quadratic in the field, then obviously we will not just get an operator O, which has no field dependence, but we will also get a contribution which is still linear in the field. Now, if we repeat the expansion of an expectation value now of such an operator, we will again get an unperturbed contribution where we have the field-free operator and the unperturbed wave function. And we will get now two terms which are linear in the perturbation, the one which we just had derived with our linear response function here, which comes from this term. And we will also get a term which comes from here. But since this is already dependent on the field, this will just be an expectation value again. So we'll see our linear response of our expectation value of a field-dependent operator will then have two contributions, a linear response function and a linear response function of the term which comes from the first order Hamiltonian, and an expectation value from the operators which comes from the second order Hamiltonian. And we can also look at the static case again, and there we will again get just the expectation value here with the unperturbed wave function, and we get the static linear response function. Now this expression or this expansion for the static case, we can then compare with the equations, which was equation 336, which we had derived in chapter 3.3 on time independent response theory. And if you compare, of course, here we have the unperturbed expectation value. Here we had the expectation value on the first order correction to this perturbation dependent operator, which is just this one, multiplied with f. And then our linear response function multiplied with the corresponding component of the field, of course, is just corresponds to these two terms, so it's the same as these two terms where we had the expectation value of the operator with the zeroth order wave function and the first order correction. And this, of course, is just the time-independent static version of the expansion with which we started this chapter. But from the comparison of this part with this here, we can then also identify our linear response function as being the derivative of these two terms with respect to a component of the field. And one can also, drawing in the results from the chapter on the density matrices and perturbed density matrices, we can also identify the linear response function here as the integral of a property operator here for the one electron case, because this is just an integration over one particular electron. And here we have the perturbed reduced one electron density matrix. So much about the first order corrections to the time-dependent perturbed expectation value of our property operator, so the linear terms. Now let's look at all the second order terms in the expansion of the time-dependent expectation value. And there we will have three terms because obviously in the expansion we can get a second order term if we have a first order wave function in the pra and in the ket, and then we'll get two second order terms where we have a second order wave function either in the pra or in the ket. Now we can again insert the correction to the wave function, which we had derived in the chapter on time-independent perturbation theory. And here we insert twice the first order correction to the wave function. We have to make sure that in the integrations over time we use two different time variables. So we have t prime and t double prime. And here in those two terms we insert the second order correction to the wave function, which also included two integrations, one over t prime and one over t double prime. Now all these three terms, after we inserted the correction to the wave function, can actually be combined by making use of commutators. And you can see we have here not only one commutator, but we have a double commutator. So by making use of this double commutator, we can combine all these three terms in one expression here. And this expectation value over the double commutator of our property operator in the interaction picture, and actually two perturbations, twice the first order correction to the Hamiltonian, twice the first order perturbation in the interaction picture, and once at the time t prime and the other one at the time t double prime. And so we have now two integrals from minus infinity 1 to t here, where we integrate over t prime, and the second one where we integrate over t double prime to the time t prime. And in both of these integration, we would like to extend again to be from minus infinity to plus infinity. So we introduce now twice the Heaviside step function here for this in this integral and here in that integral. And then again, we can insert our first order correction to the Hamiltonian, meaning write it up as the product of an perturbation operator which only depends on position, canonical momentum, spin of the electrons, and the fields. And we get twice two of them, one, and they both are still in the interaction picture, of course, because here we had the interaction picture. So one is at time t prime, and the other one is at the time t double prime. And then we get two components of the field, which we can take out of the integral over the position of all electrons and put them in front of here. So again, this second order correction to the time-dependent expectation value, or in the expansion of the time-dependent expectation value, we can write up as a product of now two components of the field and this quantity here. And this quantity in parentheses is called the quadratic response function, because it's the factor which is multiplied on two fields, quadratic response function, and written in this response function notation here with the double brackets. It's written up like this, where you can see now we have still our property operator P here at the first, and then we get a semicolon followed by all the operators representing the interaction with the different fields which we have. So in this case we have two fields and they're separated by commas. And the definition is once again written up like here. And similar like the linear response function, also the quadratic response function, which here looks to depend on three times, t double prime, t prime, and t, in reality only depends on two time differences, and that is t double prime minus t prime is the one time difference t2, and the other one is t prime minus t. So in the same derivation we can write this now to be just the linear response function of P, and then the two perturbation operators, where one is depending on the first time difference and the other one is on the second time difference. Now this expression here is an expression for the quadratic response function in the time domain. And again, we would like to also define a linear response function in the frequency domain, which we can obtain from the expression from the time domain by figuring out the Fourier transformation. And I've done that for you here. So here is the expression, is our quadratic response function in the frequency domain, and of course this depends now on two different frequencies. We had two times before, so now it's two different frequencies. And making the Fourier transformation and using that we know the complete set of eigenstates of our unperturbed Hamiltonian, meaning these functions psi n in addition to the ground state psi 0, we can write up this sum over states or spectral representation of the quadratic response function in the frequency domain. And now we have three transition moments. Up here in the numerator, we have one from the ground state, our property operator, to one of an excited states, and again from the ground state with our perturbation operator to another excited state. And then we have one transition moment, which is between two excited states in each of these terms, between two excited states, and over the third operator. And the bar here means that this is actually not just a normal expectation value and a normal transition moment between two excited states, but it's the value of the transition moment between the two excited states n and m minus the ground state expectation value of the same operator. In total, I have written up here three terms, and you can say they differ by which operators are in which of those transition moments. And they also differ by which frequencies we have in the denominator. And in reality, there are 6 terms, but in order to make it more compact and fit on the slide, I used the perturbation operator. So we get all the other terms, the terms 4, 5, and 6, by interchanging frequency 1 and 2 in all of these terms. So here we will get, well, that's the same, but here we would get a term where we would have omega 1 here, the same here we would have omega 1 and omega 2 here interchanged, and here we would have get omega 2. And as I already mentioned, I mean, here we have two different excited states, and therefore we also have a double sum here, not only a sum over all the excited states n, but also a sum over all the excited states m. And in these energy difference denominators, now we have either the energy difference between the ground state and one of the excited state, or the ground state and the other excited state. Now combining now our linear response function and quadratic response function, we can write the expansion of our time-dependent expectation value of an operator. Here and again, here I assume that the operator is perturbation independent. We can write it now up to second order. So we have our unperturbed expectation value. We have a contribution or correction to it, which is the linear response of the expectation value, depending linear on the field with our linear response function here in the time domain. And the next term is then quadratic in the fields, or depending on two fields. And we have the quadratic response function. Or in the frequency domain, where again the time independent unperturbed term, of course, is just a normal expectation value. And then we have here an integral over all frequencies with our linear response function in the frequency domain. And here we have the next in the quadratic term. We have integrals over two different frequencies, and we have our quadratic response function multiplied with two field components, which can be at different frequencies.